Software Engineering Radio episode 34, Enterprise Architecture. This episode is an interview with Andy Longshaw. He's one of the two authors of a book on architecting enterprise solutions, patterns for high-capability internet-based systems. And so this episode will be on this topic, obviously. So welcome, Andy, and why don't you start by explaining a bit of your personal background and your background.
Okay. Yes, I've been working in software for 20 years. Came up through the route of being things like system administrator and low-level coder, through to the status of principal technologist at QA training, which is the grand title. And then going on to do some more real-world stuff, hands-on design of systems, and getting to the gradual realization that technology wasn't the solution, that the technology was really part of the problem.
So then I guess this book is not about a specific technology, but rather, as patterns are usually, about the principles and the core building blocks of how to build these kinds of systems.
Yes, that's certainly one of the key things here, is that no matter whether you're using J2EE and Sun hardware, or whether you're using Microsoft software and Intel-based hardware, the things that you're doing in this area are fundamentally the same. So you should really understand your motivation for doing what you're doing before just picking a technology and saying, oh, look what we can do with this. It's like, no, why are you doing that with that? It's we don't know, but it just looks good.
So before we delve into the patterns, can you maybe briefly explain what the core characteristics of this particular class of systems is? What's an internet-based high-performance enterprise? I think that were the buzzwords. System.
Yes, I must apologise for the title. We struggled with that as to what between publishers and authors as to what the book should be called. I mean, the key angle that Paul and I came from is about non-functional requirements. So there's scalability, availability, performance. Primarily, but also a variety of other non-functional, such as maintainability and extensibility. This set of patterns originated when we were doing a small amount of work on a training course that somebody wanted to write at Sun, and the course led nowhere. But while Paul and I were working on it, we started getting all these sort of ideas of how to view the world we've been working in, of putting together clusters of servers, distributing software across those servers, and having to deal with variable load and so on and so forth. So we started to think of the illities or system qualities, and the fact that to a greater or lesser degree, your functional requirements, fine, you capture your functional requirements as use cases or user stories or however you like to do that. And essentially, you could run on your functional system on one box. It's only the non-functional requirements that start to make it distributed and dynamic, and you get into failover and all the rest of the stuff, that suddenly you start to get a whole set of tricky problems. And it changes the way you architect your system, certainly. And in many ways, it changes the way you write your software.
Okay, so then I guess we should get started with the first pattern. It's... As I can see, I've read the book, but that's a while ago, so we're taking the book as a kind of cheat sheet for me. So the first pattern is called Application Server Architecture. Sounds rather general, but I guess that's the point. It's the starting point for the detailed patterns.
Yes, we went through several tortuous iterations, and we'd initially tried to classify the patterns in some way, because we knew it made sense to have it manageable and split them up somehow. And we'd fairly quickly come to the split of performance patterns and maintenance sort of evolution patterns and control patterns, and those three classifications. But there was something lurking around of like where you actually come in, and we figured out that essentially this made sense once you decided that essentially your software was going to sit pretty much in one housing, so one runtime. And then you then get instances of that runtime, either multiple instances on the same machine or instances on different machines, and you start to load balance across them, fail over between them, and so on. So that's where the application server architecture came from. This thing of saying, rather than having a dedicated, say, payment server over there, a dedicated shopping cart server over here, a dedicated content management server over here, that essentially a lot of the systems we're working with, all of the functionality was put onto one server instance. And the way you achieved scalability, availability, and so on was by repeating instances of that combination of software.
So if you talk about application server architecture, then you don't mean that you should use a J2EE application server, but rather that you have a certain setup of components or applications running on that machine, and that thing can be easily replicated. Is that what you're saying?
Essentially, yes. What we find is that if you're dealing with these sort of internet technology-based systems, so it's almost like when you come in as a starting point, you say, right, my systems are out to a large, potentially variable group if it's across the internet. I'm using HTTP, HTML, ... Therefore, I'm going to have JSPs or servlets if I'm working in the Java world as my front end. And therefore, I need something to house those in, and therefore, I've got an application server. And in the Microsoft world, it's pretty much the same thing, except for the fact that the application server is really hidden as part of the operating system, and then you get the .NET framework on top of that, and that provides you essentially with the same sort of application server.
So the core element is the application server, and then can you actually really run all parts of an enterprise application on an application server, or do you need some special kinds of things?
Well, this is the key issue, is that not everything fits in the application server model. The application server model is very driven by user events. So a user comes in, hits a particular page or a particular piece of functionality, and that triggers the processing. There are other things that want to happen in a system. So in an e-commerce system, you may well want to mail out to your customers. So you're dealing with the same data, people who've been to your website and registered, and you want to use the registration information and so on, but the actual trigger for that event is completely different. It's a time thing that once a day or once a week you want to send out a bulk of email to those people. And so really sitting that in the application server, if you tried to put that in the application server, you start to get into tortuous triggering mechanisms that the application servers really weren't designed to work with. So that's where you get onto the idea of the peripheral specialist elements, that these are things that are designed particularly to do a job that doesn't fit in the same, it fits in the style of the application server.
One thing that I find interesting is that so you wrote a book about patterns for enterprise applications, and they contain patterns, as we'll see in a moment, for all kinds of things like performance, scalability. And still you say you should run things on an application server. Now, if you ask the application server vendors, they'll say, separation of concerns. You just write the business logic, and then the application server takes care of all those non-functional things. And from reading your book and from talking to you, I get the impression that that's not completely the case.
Well, there's definitely several angles to this. One is that there's inside the box and outside the box. So inside the box being inside the application server. So when you're inside the application server, the separation of concerns is a good idea, because you don't want just a bunch of spaghetti code inside your application server. However, once you start getting to the levels of machine management, then having separate machines to do different jobs. You've got to balance different forces. So you've got the question of whether you're actually utilizing the hardware correctly. I mean, we listed out our set of non-functional non-functional characteristics such as scalability, availability, and so on. And really, the key one that it's almost like the requirement nobody dares speak of is cost. A non-functional requirement is probably one of the biggest. Cost is probably one of the biggest non-functional requirements in any project. And so if I were to say, well, great, we'll separate concerns and we will have dedicated web servers, dedicated business object servers, dedicated database servers, and so on. And of course, each of these has got to be available, so we need at least 2 machines for each of them, and so on. Suddenly the cost starts to skyrocket. in terms of hardware and in terms of ongoing support for the hardware. So that's why there's a balance to be had between what should be specialist peripheral and what should be in the application server architecture, because the application server architecture then can do a variety of jobs while still running on, say, 3 machines. You can still get the right level of availability from 3 machines, and they're all running at a reasonably 60% usage rate most of the time, which managers like. They like to see that the money they've invested in hardware is being used a lot of the time.
Okay, so let's move on to the first section of non-umbrella patterns, the real stuff, which is called system performance patterns, and I guess it deals mainly with performance and scalability issues, I would expect. So what are the main building blocks of making systems scalable and perform well?
The first thing is just to clarify, we've tended to use the term elements for things because some of these patterns apply equally to hardware and software. And if you start using terms like components, then there's a lot of overloaded meaning in the software world, and also in the hardware world. Components, people tend to think maybe down to chip level components and ICs and so on. So we came up with this term of elements as a compromise. So we talk about things like active redundant elements. So when we looked, probably the 3 key ilities. Software qualities system qualities in this area are performance, scalability, and availability. So the active redundant elements addresses really availability. To say, okay, I have a machine. Again, I could start off with one single machine. Great, it does all the functional things I need. But then if it falls over, my users haven't got any application to run. So what can I do? Oh, okay, the easiest thing I can do, to a degree, it's a bit like, okay, what's the simplest thing I can possibly do? I can add another machine that if that one falls over, the other one starts up, either automatically or it's brought online, so some manual mechanism. So that's fairly straightforward. Okay, so we fail over from one to the other. But it's then the questions around that of, is that second machine of the same capacity? Does it need to be the same capacity? And again, we get into this non-functional requirement of cost. Can we afford to have 2 machines of the same capacity? One of them that's just sat there completely idle all of the time. So that's one side of the questioning. And the other side is, how do we do this failover? So, okay, we have potentially a piece of hardware up front that is a content management switch that decides where to send that requests. So it'll send all the requests to one server, and then if that fails, if it detects the failure, then it can send them to the other server. But what if that content management switch fails? Okay, so we need active redundant content management switches. So this is why we got into calling them elements, because so there's this failover potentially between hardware devices such as that, between software servers such as the Sun workstation or the rack-mounted server that the application server is running on, and also between the software instances themselves. So potentially you have multiple application server instances running on one piece of hardware within partitioned virtual machines, and you can fail. One of those could crash, and then the load for that goes on to another one that's sitting there waiting, not doing anything. But obviously this is slightly artificial. When we get to that stage, you wouldn't really design it like that. You'd say, well, okay, why have I got an instance just sat there waiting, doing nothing? Can't I use this usefully? So then that leads on to the thinking of load balanced elements, where we've got the same sort of scenario. We have one or more what we started to term functionally identical elements. So they do the same function, but potentially they've got more or less power. So in a typical load balance scenario, you have a set of servers, say, that are functionally identical and also pretty much identical in terms of power. But there's no reason that has to be the case. Potentially you can start with a smaller server, and then as your load grows, you get more customers into your e-commerce site, you can afford more hardware, you get a bigger server, and as long as your content switch can balance between the two of them and if it's working on a feedback algorithm to know which is the more busy server and so on, then you can use this as a mechanism for lumpy scalability of your system.
And it automatically means that if one of the machines go down, the overall amount of power you have is reduced. So as in the redundant element case, where you have a slower machine as backup, and systems get slower if the primary machine fails, it's kind of the same thing in the load balance case, because if you have less total power, the application is going to get slower, but you can use your resources more efficiently in the case where nothing fails. So that's probably the core cost benefit.
Yes, definitely. The case of not having a machine or machines sat round doing nothing. And in some cases, sometimes it's difficult to avoid that. So for things like firewalls, for example, you don't necessarily want 2 firewalls in operation at one time. So you may decide that what you really want is a warm standby that is the redundant element, that it's just waiting there to come on board should the first one fail. But for most other things like switches and routers and servers, you really want to get some use out of what you paid for. But this thing, what we found interesting as we were going through this was this thing of where is the tipping point between active redundant and load balanced. There's almost, again, if you go from the technology direction, there's almost an assumption that, say, if you have a set of Windows 2000 servers, you will cluster them together. Well, why? Is that the best configuration for your particular organization, the particular application you're creating? It may be better to have a far smaller capacity server that can give a minimal amount of functionality for people that they can get by with while the main server is brought back on stream. If that's acceptable to your application, why get into the complexity of introducing something that's got to analyze the load on the servers and distribute load between them?
So now I'm a client in one of your applications. I use your application. The primary server stops or crashes. So I'm kind of magically redirected to the backup machine, or in case of load balanced elements, just to a different one of those machines. What happens to my current process, to my data, to my session? Is it replicated, or any ideas there?
It's funny you should ask that. So, yes, there are whole things to consider, and this is, I mean, you've hit the nail on the head here. That as soon as you stop having one box that housing your functionality, a whole set of other things spring up. So great, we've got a really good motivation for having multiple boxes, whether that's one failing over to the other or whether that's load balancing between. But we immediately get into the issue of, as you say, what about my session data? Because we're in the land of internet applications. We're inherently stateless in terms of there's no ongoing connection between the client and the server, so there's no way of maintaining that. Now, the water's muddied slightly because obviously in HTTP 1.1 and certain application servers, you can have sticky sessions. So potentially you could create that ongoing connection. But the question is, do you really want to? And you get into the question of, to solve the problem, one of the solutions to the problem is to make the client sticky to a particular server. Then great, your state is always there. The problem being, if that's the server that falls over, or if that's the server that's really heavily loaded, you either have no performance or poor performance. So in order to deliver a high level of performance and scalability particularly, you need to be able to move clients between different servers. And in doing so, you need to move their current session state. So you get into this thing of, great, as in the simple system, we can maintain our session in memory. That won't work because we can't transfer it across easily. So there's got to be something that's shared between the systems that they can all see in order to hold this state. So that brings us on to the concept of having to have a common store, and that store for persistent information, so common persistent store. So sharing between the application servers a repository for that sort of state. And again, this then brings up questions. Where does it live? It could be one of the application servers. Okay, that's a fairly simple, fairly straightforward thing to do. But two things. One, it doesn't fit with the style of an application server. And if that application server happens to be the one that crashes, everybody loses their state. So we again get into this thing of, okay, well, we've got to have something that's not one of the things we're expecting to fail, so not one of the application servers. So fine, we can create ourselves a database server. So we decide to put it in a database, or potentially just on a some sort of RPC accessible state store. It doesn't particularly matter, but we have some form of state store. And fine, okay, so that lives on a separate box. Great, okay, so if any of our application servers falls over, they can all go back to the same source of state. Okay, a couple of issues now then. One is that we now have another single point of failure, which is our storage, our state storage box. So we then have to apply the same principles there. We say, okay, well, what do we want to do? We can have an active redundant state storage, or we can have load balanced state storage. Let me just back up before herring down that line. What happens to the state? You know, we've got, so when a client request comes in, we're obviously dealing with that in memory. We've got variables in memory. We've got that we know which customer we're dealing with. We've picked a cookie up off their connection, so we've managed to identify that customer. But given that our state is on that separate database or state server now, how do we get hold of it? So we've got to make database calls or RPCs across to the state server to retrieve the state, and we've also got to make sure we make equivalent calls at the end of the call to push it back out again. The problems we get into there, again, another nest of problems appears below that, because we get into the question of performance. We're degrading performance because we're adding extra cross-machine calls, and also we've got different and more complex and more interesting error handling scenarios of what happens if the system crashes part way through before it manages to write the state back.
One thing I did in a system I once built or was involved in building was that we'd keep the session in memory of the sticky session machine, and we'd write it out to a database, but not whenever something changed, but at well-defined synchronization points. That would mean that if the current machine crashes, you would continue your session not exactly at the point where you left, but at a well-defined save point. So that was a compromise between having users not lose any data and the performance penalty you'd have to pay if you'd write back everything to the database.
Indeed, and that sounds like there's a good sort of trade-off there between the amount of performance you bleed through writing everything back and the amount of benefit you get. You can't say that you should always do X. And this is one of the key things here, is that if you have a technology out of the box, it's tempting to say, you look at the prescriptive guidance from the vendor, and they say, this is how you build this sort of application. And it's like, well, okay, maybe this is how you build this sort of application if you are eBay or if you are Amazon, because they tend to show a top-end sort of application with all the bells and whistles and all the failover and all the load balancing and everything else. The problem is if your application is somewhere between very straightforward one and Amazon, you need some of the things, but not all of the things. And the trade-offs, you need to figure out what trade-offs you can make yourself. And that's, as you say, that sort of thing where, is it good enough to have a session from about 5 minutes ago? If your state doesn't change that often, yeah, great. For the one person it inconveniences, the 1,000 who never notice will carry on working quite merrily. I mean, obviously, so we're talking about common persistent stores. We're getting to other things. If we're saying that our common data store has to be duplicated in some way, either active, redundant, or load balanced, we get into the question, if we've got two instances of it, how do we know which one's got the right data? So we get into the fact that we have to have data replication between the two instances of the data store. So we don't go deeply into styles of replication and issues around replication per se, but the data replication pattern we have in there fits in with the active redundant elements to say, if you have data there, then you have to have data replication in order to make this work, because otherwise you'll fail over to something that's so far out of date, your users aren't going to accept it.
Is it fair to assume that your database will take care of that? Because I often see those pictures where it says database and Oracle will take care of the replication. So are they mature enough? So is that a valid point?
From the systems I'd worked on, I would say yes, but again, your mileage may vary. I have fairly straightforward, or I've had fairly straightforward requirements for state management in the business systems that I've worked on. So the amount of replication you get out of the box from something like SQL Server or Oracle has done the job quite adequately. Obviously, if you get more complex requirements and you've got different data centers and so on, then everything becomes far more complex. And the solutions I've seen where you have, say, like multiple data centers, the sort of solutions I've seen people put in place are more to do with having things like storage networks. So they actually address it at the file level rather than at the actually trying to get the software instances of databases to synchronize with each other, which seems to be a simpler solution.
And the replication you talk about is primarily asynchronous, so it's not like you have a two-phase commit to two database instances, which I think Oracle can do also, but rather what you're talking about is this asynchronous thing where the slave database is always 10 seconds behind or something, or did I get this wrong?
The requirements I've had have generally been addressed by having, as you say, the master-slave pairing, which parallels well with the active redundant. So your active server is running, you get a fairly powerful active server that's running all the time, and then if it does fail, it fails over to a lower power machine that has been clustered together. It's been synchronized, so it's been getting all the updates shipped to it from the master as it's gone, so it can start back up from a fairly accurate location. But again, one of the things we get into here is in both cases, and it's worse if you're trying to do multi-master synchronization. But in either case, you get a lot of you're going to have a lot of traffic between the two systems. If you're putting a lot of data into your system, all of that data's got to go across the boundary between the two database servers. So it implies more cost, more performance degradation, and so on, or a balance somewhere between the two. So you can spend loads of money so that you don't notice the performance degradation, or you accept that the performance is going to drop a little. But there are other things then we need to get into. So if we have if we're failing over onto a lower capacity server, so we can be doing this at different levels. So there's the database can fail over, there's the application server can fail over, but also we identified the need to in most systems to separate out the web and the application server. Now the reasons for this, we went. It was an interesting discussion on this because a lot of systems, it was a typical pattern mining thing. A lot of systems we saw did this, but you get into the question of why? Yes. What is the reason for separating the application server and the web server? So typically you'll see the web server sitting in the demilitarized zone, the application server sitting inside the inner firewall, and so you get this two-hop thing of if somebody's coming in to request some dynamic functionality, they hit the web server, the reverse proxy on the web server drills back through the firewall to the application server runs the software, generates the results, and then it goes back through the two hops back to the client. So because you're doing an extra hop going through a firewall as well, you've got orders of magnitude more overhead than you would have if you put everything on the web server. So having drilled down through this, the two main reasons we came up with here for why people do this, primarily security. So you're moving the programmatic bit, the bit with the JSPs or the ASPs, back one level behind the internal firewall. And you can apply different levels of patching, you can apply different security measures to that machine than to the web server. So whether that's the case that you harden the web server, you make the web server absolutely bulletproof, but the application server is less secure because it's behind your firewall, or alternatively, you may take particular actions on the application server to guard against programmatic attacks, buffer overflows, and so on that you wouldn't necessarily apply to the web server. So there's a security question of pushing that dynamic functionality further back into a safer zone, and there's also the actual profile, the performance profile. Because we got this thing where you might have systems might look kite-shaped, for example. So if you imagine a kite, the traditional kite, diamond-shaped kite, if the top of the kite was your front end of your system, you have, say, like two web servers there. And if all they're serving is static content, so HTML pages, CSS, images, and so on, then even if you've got quite a lot of traffic, quite a lot of users, they can probably handle it quite well, just two of them. Whereas when you get into application servers, they're running up huge amounts of processing to churn things around. You may want 5, 6, 10, 15 of them to service your user base. So you get a certain it goes from the top of the kite, then it expands out to where the main crossbar is, and then it goes back again. It goes back to a tail again, because again at your database level you have two database servers, and so this is where we got into this thing of like the width of the kite will vary depending on the type of system, but also you may get other systems where you have an inverse triangle with the point of the triangle being the database servers. Then you have a few application servers in the middle and lots of web servers because you've got lots of static content potentially. So it depends on the type of system as to what shape it will look like.
So what you're saying is that the question of how you distribute your layers onto tiers should be determined by your basically load requirements. So if you have them on different tiers, you can load balance or you can give different amounts of power to each of the logical layers because there are different physical tiers.
Well, this gets into an interesting point here, because the actual location of the logical layers, if you take the typical presentation, application, business data, I had this real road to Damascus thing about how everything fitted together as we were going through some of this, because of coming from I suppose it's just because of the systems I'd worked on up to that point. The use of the web server had been... We'd actually had systems where the ASPs/JSPs had been effectively on the web server. So it had the web server then calling across back to the application server, which is serving things like EJBs and so on. And when you step back and look at this, you think, well, this is absolute insanity, because you're making lots of RPC calls between two physical machines. Whereas really what you need to do is, again, it's inside the box you partition logically, and the inside of your box is your application server. The only thing the web server should really be doing is feeding static content and delegating everything else back off to the application server. And so there's actually a section that discusses why tiers are not a catastrophe, which is based on a conversation I had with someone on a training course who used to say, if something was bad, it's a catastrophe. And was discussing this through with him when I had this road to Damascus sudden realization, and I find this quite enlightening in some ways, because if you read a lot of the vendor stuff, they are very loose on their use of terminology, tiers and layers and elements and servers and so on. It all intermingles, and it can give you a very skewed view of the world and how they think the world should be. And I get the feeling sometimes that somebody within Sun years and years ago probably said, hey, if you have the EJBs on a separate tier of machines, then the JSPs and servlets can talk to them, and also the thick clients can talk to them as well. And it's like, oh yes, that's a great idea, in the case that you have both thick and thin clients. But for most of us, we don't have one. We have one or the other. So yeah, if you have thick clients, you've got to have a separate tier of EJB servers. If you've got thin clients, there's absolutely no need to have a separate tier of EJB servers. And probably there's absolutely no need to have EJBs, but that's a different story.
We've had this discussion on the podcast, I guess, a couple of times. So are there any... To optimize the performance of an application server, a lot of things are obviously done by the application server vendor. Is there anything that's particularly worth mentioning with regards to things like caching or limiting the amount of users that you can use in case you're in a backup or something?
Well, as you say, you expect out of the box with any modern application server environment, you expect things like resource pooling. You need to have that in order to achieve the scalability. You need to be able to acquire late, release early. The other thing, the other thing that's useful is caching mechanisms. There's obviously data that doesn't change much over time. So fine, you want it cached in your servers rather than having to go back and fetch it from the database every time. One of the things we get into though with if we've got active redundant failover, or even in the case of load balanced, if our amount of processing power drops below a certain level, then we run the risk then that everybody visiting our e-commerce site starts to perceive very slow performance. So again, we get a trade-off scenario here. What we can do is we can limit the number of connections at the front end, say like at the web server end or the front of the application server, which means that in some of the cases then some customers coming to the site will not be able to get a connection. So it's obviously bad for them, but what it does mean is for the remaining people who are still on the site, they're getting a more consistent level of performance. So if we know that the back end has reduce its level of performance, we can wind down the number of connections we can admit in, so the people who get in can still get a responsive site, and other people get told politely, "I'm sorry, we can't help you at the moment." So that's the sort of things we need to think about at the front end. But there's also considerations at the back end, because one of the things marketing people and so on love to do is play with figures. If they want to know how many people have visited the site, what sort of patterns of usage they've made of the site, and so on. All of that is stored away in your databases, your live databases. If people are performing large queries on those databases, doing data mining, crunching, trying to figure out what the optimal paths are, what products they should associate with which other products, and so on, there's two completely different user sets there, two different sets of functional requirements on the system, one for a quick turnaround for a customer coming in from the web, and the other for a high amount of processing. So in that case, what you can do is take what we call offline reporting. Basically take a snapshot of your data, put it on a separate database, and let the marketing people play with it to their heart's content. Because generally what they're doing doesn't have to have the latest and greatest data. It's historical trends they're looking at.
And also often those databases have the same content but a different structure, or maybe the content is pre-aggregated to some level so you can run data warehousing functionality more easily, I guess. So that's not a reason to have a separate database.
Correct, yes. If you want to create particular views on the data or particular combined tables and so on, you shouldn't have to put that overhead on your live production server.
Okay, so I think this completes the patterns that deal with system performance. Performance, as I learned from the discussion now, also performance in the sense of availability. So it's basically could be called runtime patterns. Whatever. So anyway, so the next kind of patterns we want to talk about are the system control patterns. They probably have to do with the idea of keeping the system up and running and monitoring and these kinds of things.
Yes, so this is one of my personal soapboxes. The things about scalability, availability, and performance tend to be what I call front-end stakeholder concerns. So in any system, you have the users of the system, you have the sponsors who are paying for it, you have the version 1 development team, all of whom have an interest in the first version of the system, and they're the front-end stakeholders. And generally, their requirements are listened to and generally met. What you then have is a set of what I call back-end stakeholders, so the operations team, the support team, and the version 2 onwards development team, who've got to live with all the stuff that was put together in the first place. And this is where you get into and also not only that, but they've got a live system to deal with. So they're responsible for keeping that system going. So if things go pear-shaped, it's not going to be any of the front-end stakeholders that get hauled out of bed at 2 a.m. in the morning to come and fix the system. It's going to be one of the back-end stakeholders. So they have a set of very, very legitimate concerns about what requirements are in the system. And the core thing is that they need to know what's going on in the system to be able to diagnose it, which is where we get into initially continual status reporting. So the idea that every component in the system should be capable of reporting its status of what's going on inside it. The amount of information will depend on the component, the type of component, and it'll also depend on the audience for the information. But basically, that's the core basis of continual status reporting. On top of that, then, obviously, fine, things are generating information, but what does it mean? So what we need to draw out of that is it operating correctly? There are different levels of this. Has it stopped working completely, or is it nearing its capacity? In which case, we start to need to take measures about it. So that's where we get into the operational monitoring side of things, and using that continually reported information to provide us with the basis for that monitoring and alerting should things fall over or go beyond thresholds. So that operational monitoring and alerting is more event-driven. So that's an event-driven part of the system that you assume the system's going okay unless it pops up and tells you that it isn't. You then get the other side of the coin of, well, you actually want to know how the system's doing. This could be from several aspects. One is from the operations point of view, you want to see when things are warming up. You want to see the profiles, the trends of what's happening across your servers. The only thing is, you don't have time to wade through all the logs. So what you need is some representation of what's going on. So this is where we get into the idea of having a system overview, because really what you need is an at-a-glance view of how your system is running, with indicators of like red, amber, green indicators. So everything's green. All the application servers are green. Oh, the web servers are amber. I wonder why that is. Let's go and have a look at the logs. So it gives you start from the top level, where to drill down into, what needs looking at the moment, which you would never get if you have to wade through the logs yourself.
How would you say, how much, if you build an application like that, how much of this monitoring, logging, alerting stuff is something you have to do yourself? How much do you get for free by application servers or SNMP tools or HP OpenView or whatever? So how much out-of-the-box functionality can you get there?
I think it's there is a reasonable amount of out-of-the-box functionality, but if you get, say, like hardware, pieces of hardware like routers, they're generally very well served for SNMP and so on. So you can now, you've got a fairly well-defined object model, whether it's CIM and things like that, where you can hook it up to things that are already built to take that information, and you can just configure it on the device itself, and away you go. It gets more tricky when you get to the application level, because then you're into the area where you're reliant on individual coders, in many cases, to do the right thing in the code. And this is where it's interesting. One of the papers here at Europlop is about logging, not so much the mechanisms of logging, because that's been covered very well previously, but more what you log and when you log it, so the information you log. And it's that sort of thing. And we touched on it briefly with a pattern called 3-category logging. But the guys who are presenting the paper here, they're taking those sort of ideas on far further, to figuring out what you should log based on what the audience is, because there are many different audiences in your application.
Okay, so now you notice that something's wrong. You see an alert that you have too many users, which is good, by the way, maybe too many customers. But so what do you do? Do you need capabilities of dynamically changing some aspects of the configuration, or what do you do about it?
Well, this is a good question, because it's in the security world, they talk about the detection of an intrusion, and the fact that, great, okay, we can put up all these things to detect something that goes wrong, but if we can't do anything about it, what's the point of detecting it in the first place? So what we need to be able to do is be able to configure the system based on what's going on, to change the values of things. As I mentioned earlier on, if you want to throttle down the number of users, if one of your servers has fallen over at the back end, then you need to be able to do that at runtime. You can't reboot all the servers. Go in and change a configuration file and reboot the server. No, that doesn't work if you've got a highly available system. So you need to identify key values, key parameters to your system, and make them dynamically adjustable. So you can go in and, say, change the value in a database that's read on a regular basis, or have a refresh mechanism. Like this, trying to remember which one it was now. It's a long time since I used Unix, but there's a particular kill signal on Unix to get things to refresh themselves, to reread their configuration parameters. That sort of mechanism, in order to be able to change the running system. Or
in Java, maybe use a JMX dynamic configuration for this kind of stuff.
Yes, and there are many ways of skinning a cat in this case, and the complexity and sophistication will depend very much on whether how much of this you need. It may be good enough just to have a couple of values in a database and rely on the fact that the next time the component is instantiated, it picks up the new values.
So, and just since we already mentioned Europlop, and this interview is actually recorded at the Europlop 2006 conference in the Kloster Irsee in Bayern, Germany, there is another paper by Paris Avgeriou about dynamic reconfiguration in service-based systems or something like that. So he talks a bit about this idea of monitoring, evaluating the problems, and then adapting the quality of service. Just as a side note, we'll put it into the show notes. So the next one is probably related to security, I guess, because we didn't talk about that too much yet, and I think it's an important concern in enterprise systems.
We lumped together the sort of maintainability, the operations issues, together with security, because security spans. You've got to think of it up front, but it's also something that's an ongoing part of the system, that you may change the security model, the security levels, certainly over time. So we started. The most obvious pattern that people use in terms of internet security is the demilitarized zone. So the idea of an external firewall stroke router, an internal firewall stroke router, and something between that will serve the outside world, and is potentially like a sacrificial area. It's things you put in there have got to be either expendable or more highly armoured than your internal servers. So that was the primary defensive security for the systems that we'd worked on. You get into other issues with if people are trying to break into your systems. One of the things that can give them a real boost is if they can get an idea of the topology of what they're trying to break into. So if you have well-named servers, for example, directory server, web server 1, web server 2, web server 3, database server 1, database server 2, and so on, then great. It's great from the maintainability point of view. It figures very highly. But from the security point of view, it's less good because it gives people an easy ability to map. All they need is the names of your servers, and they can map out what functionality is on each one and start to try and guess how to break it. So that's one of the things we address with a pattern called information obscurity, of saying, well, potentially these, by changing the names of these servers, then it will be less accessible. They make your system more secure through obscurity. And the same sort of thing applies to, you can take that all the way down to encryption of credit card details and so on, of having some, those are probably the two ends of the scale, but some way of obscuring the data that you're working with. It all adds an overhead. So obviously in credit card encryption, you've got to decrypt it in order to use it, so it's a processing overhead. And as I said, in the case of obscuring names of things, it's a maintainability overhead. So that was the other thing in terms of static security that we noticed that had been used on systems. The other two things were to do with data in transit. So the key thing, essentially SSL and its relations. We said, okay, well, what are you doing here? Again, looking round, at that time there weren't many security patterns. So this was before Marcus Schumacher and company started to put together the security patterns book. And so we looked around and we couldn't find. This is a general theme. We were quite surprised that nobody had put together patterns in this area before. So in the same with the security, we looked around and we thought, well, nobody's actually put together a pattern about SSL to describe essentially the core principle behind SSL, to describe why we do it, what the forces are in terms of wanting to create a secure connection, but there's an overhead associated with creating the connection and so on. So we put together a pattern called Secure Channels to discuss that, and also known partners to discuss the more secure VPN type networks where you've got a business partner connecting in and making use of your systems again across public internet, and therefore needing to get involved in authentication with using certificates.
Okay, so I think looking at our concept for the show, this completes the system control patterns, I think. So we have built a system that runs nicely, that's reliable, that's fast, that scales. We have a means of keeping it running, monitoring, alerting people, changing stuff dynamically if things should go wrong. So what's missing, I guess, is a way of evolving the system over time once requirements change. So there are probably a couple of architectural building blocks that you can use to make a system potentially adaptable over changing requirements or just over time.
Yes, I mean one of the hardest things I've found over the past few years is getting out of business people a correct estimation of the number of customers they expect for internet-facing websites. They will either be wildly over-optimistic and over the top, or they'll be understated. And so whichever, if you tend, as an engineer, you tend to sort of try and cut through this and figure out what the real figures are going to be. But you realise that potentially there could be a very successful marketing campaign that suddenly your load starts to rise over a very short period of time. So you need to be able to adapt your system in a very quick way, but also you need to be able to extend and expand your system over the course of years in a predictable way. So one of the things you get into in terms of the short-term evolution of the system is we've talked about having scalability through having, say, 3 application servers and a content switch in front of them, channeling the load to whichever's the least lightly loaded. Obviously, at some point in time, if we're successful, we will start hitting 60, 70, 80% usage on all 3 servers, and we want to add a 4th server. And equally, if one of the servers goes down, we want to shove another one in there fairly quickly. Now, what the issue there is that the system that's doing the load balancing needs to be able to identify that there is a new server there and to start using it. So you get into this idea that you need to have dynamic discovery of the system elements. So a new element pops up. We stick a new machine in the rack. We plug it into the network, we power it up, and we want the content switch to say, aha, new system, right, here you go, here's some users for you, and off you go. So that applies at a variety of levels, from hardware to just down to the components. If you've got a new type of component, if you have a consistent interface for your components and you plug a new type in, then you want the system to recognise it and start using it, start making it available, rather than again having to shut the system down in order to bring it back up again. So that's one approach to evolving the system. Another thing is, obviously, if we've got our 3 servers, we go back to our 3 servers hitting 80% load. Another thing we can do is we can stick more hardware in them. One of the tales that Paul told when we were discussing the book and we were working through our experiences was about where he was trying to figure out how best to make an application more memory efficient, because they were running out of memory. The early prototypes, they knew they were running out of memory. So they did a few initial investigations, and they realised the easiest thing was just to buy more memory. Stick more memory in, because they had memory slots. So this we get into the idea of expandable hardware. So rather than, when you're buying your initial hardware, rather than buying a fully kitted out, fully slotted up machine, and then having, as soon as you hit the performance boundary on it, you've got to throw it away, buy one that's got additional slots. So it may be a little bit more cost to start with, but the incremental cost of having to throw the first machine away and build another one, you've got to buy the big machine anyway, and you've got the problems of any sort of rebuilding exercise is always dangerous, because you've got to be sure you're doing exactly the same thing you did last time. So that's this sort of thing. Now, one of the things that really helps in terms of evolution is what we term the virtual platform. So this isn't, unfortunately, when that first comes up, people tend to think of things like VMs. Yes. Now, what we're thinking of here is more like a set of APIs, if you like, for a platform. So one of those APIs could be J2EE. Equally, one of those APIs could be .NET. Although you probably get less benefits from .NET than J2EE, in the fact that putatively you can replace your J2EE application server with a different one. To get away from the actual virtual machine and framework side, think about something like a mail server. So on Windows, there's the MAPI API. So if we needed to do the mail out, so I mentioned earlier on that potentially your system may want to mail out to all the e-commerce customers. If we want to do that, we need to talk to a mail server to do it for us. Now, if we say, okay, our software that does this talks to the MAPI interface, then potentially the actual particular mail server behind that we can just replace with a different one, should we find that there are problems with it, either performance problems or functionality problems. So it's creating this virtual set of APIs that insulate your application from the underlying particular platforms, operating systems, and so on.
Which could be called a technology-independent architecture, just to reference.
Indeed, to reference your paper. Yes, it's
okay. So one thing we didn't talk about yet, but something that I've seen in many projects, is that people talk about staging environments and testing environments. So you have several installations of your system, one for playing around, one for verifying that it's production ready, and then the production system itself. Any specific thoughts on this one?
Well, one of the problems you get with migration is that you've got to be absolutely sure, if you're migrating from one environment to another, that the test environment, for example, you've been working in is a fair representation of the live environment you're going to be deploying into. So obviously, as you say, people employ a staging environment that is a pretty much live, pretty much exact duplicate of the live environment. So the question you get into is, how do you make an exact duplicate of the live environment? And one of the approaches here is to actually host your staging environment on the live production servers, but partitioned. So, for example, if you're on AIX, you'd have a different Unix instance. So, fine, if the staging environment went pear-shaped as you were warming it up, then it's not going to affect your production server, the service. Now, so again, this is it's a particular approach. So you may not be able to take this approach depending on what sort of hardware and software you're running on. But it's if you can do this sort of thing, then potentially what you can do is you create your staging environment there. You deploy your new version of your software. You go through your sanity checks and make sure everything's working okay. And then what you can do is you can migrate your user base across onto that new software on what is putatively the staging environment.
So in effect, what it says is, after you've verified that something works as advertised, you don't want to do another you don't want to change things again, but rather just move make this formal test environment or staging environment to be the production environment from there on, because you verified that this one works.
Yes, and that's the great benefit of it, because you've got to that, as you say, you don't have to change things again, because every time you change things, there's obviously risk of getting it wrong, and so then once your users have all migrated over, what you tend to do is you tend to clean up what was the production environment, and that then becomes the staging environment. So this is the swappable bit. So basically you're swapping backwards and forwards between typically two application server instances running on the same piece of hardware. Now you obviously get issues about the fact that if you actually start running stuff on that staging environment, its impact is taking up some resources that could be used for production. But the whole idea with the staging environment should be just a sanity check that you've got things right. All your performance testing and everything else should be further back downstream before you get to the staging environment. So that's one thing in terms of the partitioning of the system. And then the final thing is about the data. When we're looking at evolution of systems, one of the things you get is if you need to upgrade your system because your configuration data structure has changed, so you're adding new functionality, maybe your actual user data structures haven't changed, your schemas haven't changed, but the data the data used internally to the application, its configuration information has. If all your data is held together, intermingled, then basically you've got to hit the whole database and upgrade the whole database. And even if you're not hitting those particular tables, there's always a chance you'll screw something up, and then you've got to have rollback for that user data. And the problem with the user data, or the problem with what we term the internal stuff, the configuration stuff, system managed data. So it's data that the system itself originates, and potentially you can recreate. The problem with the rest of the data is potentially you can't recreate it, which is why we need to get into backups and so on. But even then, we don't want to damage it if we can help it. So if we separate out the externally sourced data from the system managed data, it means that potentially we can upgrade the system managed data database completely independently of the externally sourced data. Which means we're reducing the risk profile here quite a lot. And one of the major issues I have with the system I'm working at the moment is the fact that it's a hosted system, and it bundles the user data together with the system managed data, and this is causing us all sorts of problems because we can't migrate the two separately.
Okay, so I guess this summarizes roughly 50 minutes of enterprise architecture. Of course, it's quite unrealistic to have the wisdom of enterprise architects put into 50 minutes. It's even probably a bit more realistic to put all this wisdom into a book, and the one from which we basically scrapped this podcast. So as a kind of last word to the listeners, do you want to say a couple of additional words, which benefits people would get if they would read the book? Because the book has a couple of additional sections we kind of didn't cover in this podcast.
Well, I think one of the things we tried to do with the book was to walk through how you would actually apply the patterns. So trying to take 3 or 4 different scenarios and actually look, given those scenarios, which of the patterns you would apply. Because one of the things we're not saying is that here's a book full of patterns, go away and apply all of these in the next system you build, because some of them will apply to some systems and not to others. So we hope that by doing the walkthroughs, you'll be able to identify a system that's similar to the one you're working on, and to get an idea of which of the patterns are probably most suited to your particular situation.
Okay, so as you might have got the point, you should buy the book. So Andy, thank you for being on the show, and thank you.
Marcus, thank you.
Thanks for listening to Software Engineering Radio. If you want to get more information about Software Engineering Radio, or if you want to give us feedback, please go to our website at se-radio.net. You can also contact the team at team@se-radio.net, although we prefer entries in our comments system on the website so other people can see what you think. Software Engineering Radio wants to thank Henning Pauli for the intro and outro music, as well as Libsyn for providing the bandwidth. This episode of SE Radio, as well as all other episodes, is licensed under Creative Commons license. See the Software Engineering Radio website for details.